Right, welcome back. Video number 4 on Lambda Calculus, I believe. And we are at a point where we are discussing semantics of Lambda Calculus. And there were 4 concepts to be understood in the semantics. We have covered 2 and the last 2 are remaining. Okay? So the first 2 we already covered are the free and bound variables in Lambda terms, and also the alpha equivalence, where we just rename or give a new name to the parameter in a function abstraction. All right. So the third one, the first 2 are relatively simple ideas which we have been using in programming in general. Okay. This third one called substitution is something we don't do explicitly when we write programs, but it implicitly happens even in your Java, Python programs and so on internally by the compiler. Okay. So this feature or this concept of substitution is at the heart of how functional programs are executed by the computer or by the compiler. Okay, or the code produced by the compiler, how it executes functional programs. So this is really basically tells us the meaning of the functional programs, right? Because the meaning of a Lambda term is exactly what happens when you run it, okay, and what output you see. Okay, that's the meaning. Okay, there's no deep meaning. Okay, like in philosophy, we have a very deep meaning of life and why am I here and so on. You see, those are deep questions. But this also, in some sense, deep or intricate in some sense. But basically, we want to know what it means when you write a program and run it, right? All right, substitutions. So substitution is defined for free variables. Okay, so that's one important point. Okay. You can only substitute a free variable. You cannot substitute a bound variable. Bound variable has a very specific meaning, and we saw that in the alpha equivalence. It is really bound variable is nothing but the name of the parameter, and it's just there sitting there. And when something gets called, that's when the bound variable gets a value, right? So that's the process we are discussing now. When a function is called, at that time we have to make some substitutions, you see, for the bound variable, you see. Yeah. So the concept of substitution is defined only for free variables, okay? And the idea is we will substitute a free variable with, we'll replace. The replace is another word used for substitution. We can replace or substitute a free variable with a lambda term, okay? So what are we replacing? By is different here, okay, compared to the alpha equivalence. In alpha equivalence, you are replacing one variable by another variable, okay? One name by another name. But here, this concept is very different than the alpha equivalence. Okay, here we are replacing a free variable in a lambda term with or by a lambda term, another lambda term. Okay, so the variable is what we replace, but the new value for the variable can be a complex lambda term. Okay, all right. That's the second point, and the third point is why is this needed? Substitution concept. It will be used to define function calls. Okay. Basically, how to execute a function call. Okay. In particular, when you make a function call, you have a formal parameter and an actual parameter. Correct. The formal parameter is the x sitting next to lambda, and the actual parameter is the term provided by the user or the programmer when you call the function. Correct. So this substitution concept has to do with the actual and formal parameters. Okay. So here's an example, not in the Lambda Calculus, but in Java, Python. Okay, suppose that you had a same function we saw a little while ago. Okay, in the previous video, is prime n for I. This is the prime function. Okay, it takes an n. Okay, so that on the left is shown the function, and in the middle is shown what is shown is a call to the function. Okay, so the is prime of 17 is a call you make to the function. Okay, so in particular, I have highlighted in red the formal parameters in the is prime function definition. Okay, there are 3 n's there. Okay, all of them are the same. Okay, first n is the bound variable, and the other 2 are also bound, but they are the ones which appear in the body, which are bound to the parameter. Right. So if this n, the parameter, formal parameter became 17, then both these n's will become 17. That's what we mean by bound. Okay, so they take the same value as the value of the formal parameter. Okay, And then this 17 here is the actual parameter or actual argument, right? So that's how we refer to this 17 as the actual argument. We refer to this as argument and the n as a parameter. But if you want to use actual and formal, then you call this a formal parameter and this as the actual parameter. Okay. So there are two ways to refer to these. If you want to use the word parameter, then you say formal and actual. Okay. But if you want to use two different words, you say parameter and argument. Anyway, this is just a terminology. You probably have heard of this terminology in your programming classes. Okay. All right. So now what should happen when this 17 is provided as a value for this parameter? Okay. I've shown you here on the right side a rewriting of the body. So basically this body is copied here. The body of this function is copied here. You can see that the first line is gone. Only the last 4 lines are copied here. And also wherever the n appeared, we have replaced it with 17. You see that? That's all. Okay, it's as simple as this. Okay, that's what this concept of substitution is. Okay, the substitution is when you make a call to a function, you take the body of the function, and wherever the formal parameter in that body appears, you replace those occurrences by the actual parameter. Okay, that's all. Okay, replace. Now this is a string replacement. Okay, so you're replacing the n by 17, n by 17 in these two places. So this 17 came in the place of n, and this also 17 came in the place of n. Okay, and then you got this. Now what do you do with this? Okay, obviously you have to execute it. Okay, now this is not Lambda Calculus, so you will actually have Python execute it. Okay, if this was given to Python, it will produce the 17 true or false for 17, right? It'll probably return true because 17 is a prime number, right? So if you execute this code for in Python, you should get 17. Excuse me, you should get true, right? And if you give 18 here, then we should get false when you execute this in Python, right? By the way, the substitution doesn't tell you what is the final answer. It just tells you what version of the body you have to execute. That's all. Okay, the version of the body in which the formal parameter has been replaced by the actual parameter. The concept is simple enough, right? To make it formal, we have to worry about a few different scenarios. Okay, and we will do this with examples, a couple of examples, and then we'll write the formal definition. Okay. So let's take the first example here. Okay, first is pretty straightforward. Okay. Oh, by the way, we will write the substitution, the notation as follows. Okay, we'll write the lambda term on the left. Okay, in which you're making the substitution. Okay. Now, right now, we don't worry whether this came from the body or not, body of a function or not. Okay. Right now, we are defining just the substitution as a general concept. Okay, and then later on, we will see when we make a function call what happens. Okay, but right now we are focused on just what a substitution means, or what is the definition of substitution. Okay, so more likely than not, this would be the body of some function. Okay, but we don't care about that at this point. Okay, so the lambda x dot xy is a given lambda term, and in that we want to substitute y by 5. Got it? So y equals 5 in square bracket stands for, we want to substitute, the square bracket stands for substitute. We want to substitute y, so this left hand side must be a variable, okay? And the right hand side of the equal to must be a term, lambda term. In this case it's a number, but it can be a term like in the next example, okay? But the left hand side must always be a variable, okay? So we are replacing a y by 5, or substituting y by 5, substitute or replace. I think those are two words we can use interchangeably. Where you are doing that? You're doing it in this lambda term sitting to the left of the square brackets, okay? So this is simple, right? So y, you want to replace y by 5 in the left side, okay? So here y appears once, I've shown it in red, okay? Here it shows in red, okay? So when you replace this y by 5, what does this term become? This term becomes this, right? Lambda x dot x5, okay? So that's the answer. So when you this substituted with this substitution is this, okay? Now this is not this is just an example. The formal definition comes in the next slide or two, okay? But we are looking at a couple of examples, okay? How about the next one? Next one, the term lambda term is the same, lambda x dot xy, and also the variable we are replacing is the same, okay, y, but what we are replacing by is a little different. It is uv, okay. It's a lambda term uv, okay. By the way, what you put on the right side here could be anything, okay. Well-formed lambda term, but could be any lambda term, okay. So if you want to do that, again, if you try the same thing, you'll replace this y by uv, and you would get this term, right? So far so good, no issues here, okay. But it's a trap in the sense that this substitution is not that straightforward, okay. Here's an example which illustrates the pitfalls of just blindly substituting it, okay. All right. Here's the term lambda x dot x y. Actually, it's the same term. So in all the three examples, the term is the same, okay. The lambda term is the same. The variable is also the same, so they all three look the same, okay. But now on the right side, we are replacing y by x. Here we replace y by 5, so this y became 5, okay. Here we replace y by uv, this y became uv, okay. Looks simple, right? So here y is replaced by x, so this y becomes x, and you get this, okay. No, that's not the correct answer, okay. Why? Let's see why. What has happened here, okay. What has happened here is that this y before was free, right? It was not bound to this x. That is, this y was not the same as this x next to the lambda. It wasn't the same, right? It's not. You can see that it's not the same. It's y and that's x, okay? But after the replacement, it has become the same because the new value for y is x, and now this x has gotten bound to this, okay? So this function, or whatever this was, this lambda term and this lambda term are not capturing the same lambda abstraction, okay? Got it? They're not the same functions. Now you might say that that is true here as well, okay? This is not the same function as that, okay? That is sort of true, okay? And same in the second example too. What's the difference between those and this, okay? The main difference between those two examples and this one here is that in those examples, the new value of y, okay, did not interfere with this parameter x, did not interfere, okay? Interfere means it did not contain a reference to that, okay? So that's why that substitution is valid, and you will get the correct answers, okay? But now the new value of y here actually gets bound, or sort it gets interfered. Actually, the technical term we use is it gets captured by this lambda x, okay? Why? Because previously this y was free, but now in the new value it becomes bound, okay? So what happens to a free person when they get bound? They get captured, right? That's why we use that word capture here, okay? Right? If you're free to go anywhere and then suddenly get imprisoned, okay? You get captured, right? That's a verb we use to refer to that in English, okay? Same thing here, okay? So this y variable, which was originally free, because of this new value which it gets, that same position gets bound to this and it gets captured. And when this happens, the meaning of this abstraction changes, okay? And it'll give wrong answers in Lambda Calculus, you see? So we want to avoid this, okay? So this situation is sometimes referred to as the capture case, okay? Capture case, okay, here. So we want to avoid capture cases, okay? So how do we do that is the question, okay? The answer is relatively simple, okay? I mean, actually there are two questions to ask. One is, how do you know this is a capture case, okay? Is there an quick and easy check or test, okay? Right, to see whether it's a capture case or not. Somewhat like the COVID test, right? You want a quick and fast test to check whether somebody is infected with the COVID virus, okay? Same way here, we want to see whether this particular substitution is belongs to the capture case or not, okay? A quick test, okay? Not a very detailed analysis, but a very quick test, okay? So that's the first thing, okay? And we will we'll see that in a minute what the test is, okay? And second is, how do we fix it, okay? Right? We still want to proceed forward, okay? Because this substitution I still want to apply, okay? But I don't want incorrect answers, okay? Let's look at the answer to the second question first, and that is how do we proceed, okay? So what we do is we do an alpha equivalence on the first one. All right, and you can see the main reason why the capture happened was because the bound variable x here, okay, this bound variable x happens to be free on the new value, okay, and that's actually the answer to the first question. How do we check whether this is a capture case or not? You have to check whether this variable, the bound variable here x, is free in the new value for y, okay, and in this case it is, right? This x is free in x is free in x, that we know, right? So that's how you check, okay? You check whether the variable next to the lambda is free in the new variable, okay? So that's your new a quick and easy capture test, okay? And what do you do to fix it? You do an alpha equivalence on this term, okay, the term on which you're making the substitution, okay? So you know how to do an alpha equivalence. You just provide a brand new variable name here and then replace all the x's to that. So in this case, we'll call it x prime, okay? So that's a brand new variable in alpha equivalence, x prime, and then this x becomes x prime, and the y remains the same, and everything else remains the same, okay? So what you have done is that you have taken the original term on the left side of this substitution and did an alpha equivalence, and remember, it has to be a brand new variable, okay? Correct? That is one of the conditions. This has to be a brand new variable, okay? X prime is a brand new variable not appearing anywhere else, okay? You do that, and then you apply the substitution. And when you apply the substitution now, you can just put the x here, and it doesn't get captured by this x prime. You can see that this x became x prime, and then this capture doesn't happen anymore, okay? Got it? So that's a simple, the fix is simple, okay? That is, you just do alpha equivalence on the left, the term on which you're doing the substitution, and then apply the substitution as you do normally, okay? And the test also, we have sort of got an idea, okay? The way to test whether it's a capture case or not, by the way, the capture case will usually happen, not usually, always happen when there's a lambda term here, okay? So the variable on the lambda term x appears free on the right hand side of this substitution value, okay? Let's look at one more capture example. Oops, I went too fast here. Yeah, there we go. So let's look at one more example of the capture, okay, down here in the bottom, okay? So that's the substitution here, okay, lambda x dot yx. Actually, it's a little different than the previous one, okay? I think just the y has come to the front and x has gone to the back, that's all, okay? So anyway, lambda x dot yx, actually, it really did not matter which way that way, okay? But and here's a new value of y, lambda z dot xz, okay? So that's something randomly written here, okay? Don't worry too much about what it is, okay? But let's see whether we can apply the capture case test, okay? The capture case test is that if you had a term on the left side, which is the lambda term, and the variable next to lambda appears free on the new value here. Now that's the question you have to ask. Does the x, which is the variable next to the lambda here, appear free in this, okay? So you have to do some calculation quickly and try to figure out whether it is free or not, okay? But by observation, you can see that actually it is free, right? This x is in this term is free because the z is bound to this z, but this x is free in this whole thing, okay? You can go ahead and to the definition and figure out. So this x, which is the x next to the lambda, is actually free in the new value for y, okay? And that's why we cannot blindly substitute y by the value, new value, okay? You have to do a alpha equivalence. So in this case, this x becomes x prime. So you can see that this x became x prime, this became x prime, and then after the substitution, this y became got the new value, which is this whole thing. You see? Got it. So that's only the special case of capture case. First, identify a capture case, and once you identified, know how to fix it or how to solve the substitution. Okay. Great. So now we are ready to actually look at the formal definition. So here's the formal definition 1 through 6. Okay. This is an important slide, especially if you are building a compiler or an interpreter for Lambda Calculus or something similar thing. Okay. It's an important. There are 6 rules for substitution. Okay. There are actually 6 cases, but they're actually built into 3 cases, groups of 3 here the first two, 1 and 2 are in the same group. 3 is in a group by itself, and then 4, 5, 6 is in one group. Okay, and the reason is the left hand side, the term on which we do the substitution is the same for 4, 5, 6. Okay, so let's look at each of these groups. The first group is a variable, okay, x or y. Okay, so suppose you are given x and you were asked to substitute in that x by p. Okay, so you have to replace x by p in x. Okay, that's an easy one, right? All you're given is x, and all you're told to do is replace this x by p. Okay, that's easy. The answer should be p, right? That's what the first rule says. Okay, yeah, this says equivalent, but actually this should be equal, not equivalent. So maybe if I go on the slides, I may fix it. Okay, so when you see the slides on the website, you'll see that it's been changed to equal. Okay. The second case also is pretty intuitive. If I give you a variable y, okay, and ask you to replace x in y by p, okay, that seems confusing, but it's also pretty straightforward. Okay, so I'm giving you y, and I'm saying that inside this y, if there's an x, how can there be an x inside a y? Okay, there cannot be. Okay, right? These are atomic variables. But if there was one, you had to change that x to a p. Okay, but there's no such x, so there's nothing to change. So the y will remain as y. Okay, so that's what this definition says. Obviously, the x and the y must be different. Okay, so that's the easy case. If it's a simple variable, then that's what we do. Okay. The second case, second group, which is the third case here, is also straightforward. Okay, so if you're given an application mn, and you're supposed to replace x by p in mn, this case is pretty straightforward. All you do is replace x by p in m, which is this term. Okay, and then do the same thing on n. In n, replace x by p, which is this term. And then whatever the answers you get from those two, you place them next to each other and put parentheses around them. Okay, so that's, you're passing the buck, so to say. Okay, to the m and the n. That's all. Okay, so that's the easy the product or application it's called. Okay, and if you did have the op case, you'll do the same thing. Although we're not considering the op case in this definition. Okay, now the last three cases are for the lambda term. Okay, suppose you had a lambda term, lambda x dot m. Okay, that's case 4. Okay, and in that we want to replace x by p. Okay, now this right in the first slide where we introduced substitution, we said substitution is valid only for free variables. We said this does not apply to bound variables. Okay, and this is the situation where x is bound variable, right? Lambda x dot m, and we're trying to replace x by p. And this should not change anything. Okay, so basically this is not allowed. You're not allowed to make such a substitution. Okay, which doesn't mean that you make an error report here at this point. You just say that I don't change lambda x dot m, I'll keep it as it is. Okay, this substitution is not applicable here, that's all. Okay, it doesn't change lambda x dot m, as simple as that. Okay, so you're not allowed to change lambda x dot m where x is replaced. X is the bound variable. Okay, we're not allowed to replace x by p. Okay, so this case really should not even be considered. Okay, but for formal definition we have to state it. Okay, but anyway, the net effect is that you don't change the term, you keep it as it is. You see, very much like in case 2, we did not change the y, we kept it as it is, right? Then the case 5 is case 5 and 6 are similar, except that one is the capture case and one is the non-capture case. Okay, you can see case 5 is the non-capture case. Okay, so you can see lambda y dot m is the term, and x is going to be replaced by p in this lambda y dot m. Okay, now remember that test for a capture case, we had to say that if y is free in p, right, then it's a capture case. Okay, so that's what we do. We calculate the free variables for p and check whether y is not in that. Okay, if it's not in that, oh, by the way, this x and y must be different, right? If they're the same, then you're in case 4. So that's why I sort of explicitly stated if x is not equal to y. And if y is not a free variable of p, then it's not the capture case. Then we can blindly substitute, correct? And that's what this one says. Then this substitution becomes lambda y dot, and on m you make the substitution, x by p. We don't know what m is. M may be a big formula. So inside that you apply recursively this definition, okay? And that will go deep way down and probably reach one of these two cases, and then it will replace, either replace or not replace, okay? So that's a recursive definition. And of course the last case is it's called the capture case, when y, which is the bound variable here, lambda y, belongs to the free variables of p, which is the new value we are replacing x by, okay? That's the danger case. Or in that case, what we do a alpha substitution, alpha equivalence first, and then you apply the substitution. Got it? So you can see that we have lambda y prime, and then this whole thing is the alpha equivalence, okay? And then we apply the substitution after that, okay? And actually, in that case, we actually push the substitution inside and apply it to the new version of m after the alpha equivalence, okay? So that's how we do this substitution, okay? It's a formal definition. We've already seen informally how it works, but this is the formal definition, okay? All right, so let's look at a few examples, and actually not a few, quite a few. Actually, all the way from now until the end, we are going to do, until the end of the slides, we're going to look at many examples, okay? So let's look at the first example. This is what is given to us, lambda y dot something, okay, whatever that thing is, okay? And this one is actually fully parenthesized, so you could, no parenthesis has been left out, okay? So this is easy to decipher, so you have to actually go look at the parenthesis and where it applies, and where's the application, where is the lambda term, and so on, where's the variable. So, by the way, there are three variables, x, y, and x. You can see that here. And there are two functions here. There's one lambda x here, and there's lambda y there, okay? Anyway, we don't care too much about what this means. We want to take this term, and in that we want to substitute x by this thing, okay? So the way to proceed is to go back to this previous slide and sort of keep that on. If you want, you can print this and keep it with you, paste it on your next to you somewhere, okay? So you can actually consult back and forth between these. By the way, I have memorized this, so I have this in my head, so I don't have to look this up, okay? But so you have to see what type of term the left side is. The left side is a lambda term, right? So case 4, 5, or 6 will apply, okay? Now, case 4 will apply if this variable is the same as this variable, and it is not, right? Here's a y and that's an x. So it's not case 4. So it's going to be case 5 or 6, which is the real substitution, either with the capture or without the capture, right? So now we have to test for capture, okay? So we have to see whether this y appears free in this right-hand value of the substitution. And actually it is. It's the first thing appears, and that is free, okay? So it's a very clear case of capture case, okay? So what do you do? First you rename or apply the lambda equivalence, okay? And actually I'm showing this in 2 steps, but this whole thing was in the definition was done in 1 step, both these steps, okay? But let's do the alpha equivalence first. You take this and produce the alpha equivalence here. Very simple. All you do is you take this y and change them to y prime. That's all, okay? You can copy and paste and then change, put a prime here and prime there. That's really what alpha equivalence is, okay? And then you have to apply this substitution. Now we can apply this blindly, right? Blindly in the sense that you can go ahead and replace x by this value, okay? But you have to be blindly in a sense, but you have to be careful also, okay? You have to actually apply the definition, okay? So let's see how we do that, okay? So you can see that in the body we get this part, okay? Actually starts at this 3 left parentheses and ends at the parenthesis after the x, okay? That's where the body of this lambda y prime ends, and it begins there. Let me see if I can, with my mouse, a little difficult to, maybe I did it, no, maybe I didn't, yeah. Anyway, you understand, or maybe I should use my pencil here, right? Yeah, okay. I wish there was a way to erase the whole thing. Yeah, I think there is a way to erase the whole thing. One of these, maybe not, okay. Yeah, it erases, but when I go back, excuse me, when I go back to this, it comes back, but there is a way, one of these, I guess, this one. Yeah, there you go. That's the cleaning the slate. Okay, I got it. Okay, I'm still with the pencil here. Okay, so what I want to show is the body of this lambda y prime. Okay, begins here, ends there with that parenthesis. Do you see that? Because this parenthesis is ended with that. Okay, got it. Up this. I need to get this out. Nope, not this way, but I need to go back to this. Yeah, that's right. Oh, maybe we wanted to see this. Okay. Okay, I'll stay away from writing something here. Okay, so that's lambda y. So we had to, we already done the alpha equivalence. So now we have to replace x by this in this term. Okay, so let me write this as the body. Okay, or let's call the m, right? That's how it is called. This is the m. Okay, this thing here. Okay, so in m I want to replace. Now m happens to be a term which looks like a function application. Can you see that? So it's something times something, or something next to something, right? What's the rule for that? The rule for that is you apply the substitution here and also apply the substitution there and put the results together. Okay, and that's what and then when you apply the substitution to this also looks like a product or application. Is this applied to this? Okay, now this whole thing becomes much clearer when we use trees, and I believe in the subsequent slides we're going to draw trees for these and then show you how to do this. Okay, so now since we got all the pieces here, we have to take this substitution and apply it to each of these three pieces here. Okay, to the lambda x dot x, to the y prime, and also to the x. Okay, that's what the rule number 3 was. Okay, rule number 3. I guess maybe I can use an arrow. No. Okay. Anyway, the rule number 3, which is in my head. Okay, you can look up the. Okay, the rule number 3 basically says that the substitutions can go filter inside the function applications. So it's applied to these 3 terms, and that's really what I've shown in the next line. Okay, you can see that the lambda x dot x, and then this substitution applied, and then the y prime with this substitution applied, and then the x with that substitution applied. So I have taken this substitution and filtered it into these 3. Okay, these 2 are easy to solve because in this one, this is y prime and this is x, so this will keep the y prime as it is. Okay, and the third one also is easy. X by that will replace this x by this value, and that's why you see that here. Okay, but on this one also it's easy because this is the case number 4, which is a bound variable where you try to replace the bound variable, which does not change the lambda x dot x, right? So you can see lambda x dot x, and then x is replaced by that. Okay, which should keep the lambda x dot x as it is. So this lambda x dot x remains the same. This y prime remains the same, but this x changes to that. Can you see that? So there are these 3 terms, lambda x dot x, y, and x. Of all of these 3, this x is free, and that's why it gets replaced by this in the final answer. Okay. Anyway, it looks a little complicated, but if you take this first expression and draw a tree, and I'm going to teach you that method soon. Okay, it becomes a little clear. Okay. Anyway, that's the first example. Okay, before we actually look at more examples, let's look at this beta reduction. I think there are two slides here. Okay, I believe we are sort of running out of time, so maybe we'll come back and look at beta reductions in the next video. Okay, thank you.